Hello everyone. Today we will be talking about random convolutional kernels for time series classification, also known as Rocket, and the new version of it, which is called MiniRocket. So these are two versions of a convolutional neural network that has been presented, I believe it was in 2020 and 2021. This is a method that we are going to talk about today. The beauty of this method is that it's just randomly initialized and it doesn't have any kind of optimization or parameter tweaking. So let's see what this is about. So convolutional neural networks, as you know, a CNN or convolutional neural network is a network architecture for deep learning, which directly learns from the data, eliminating the need for manual feature extraction. So you might have seen one of these lovely figures where there are so many different layers or deep layers which extract different, let's say, features from the input images. CNN are particularly useful for finding pattern in images to recognize objects, faces, scenes, and so on. And they can be quite effective. And as a matter of fact, they have been tested on so many different kind of inputs, not only images. So images, speech recognition, signal classification like EMG or EEG signal classification, and time series processes, and so many other like problems. All the applications that call for object recognition and computer vision, they actually rely heavily on CNN nowadays. So the motivation for the development of this new method is that a significant number of time series classification methods that attain state-of-the-art accuracy, they have high computational complexity, they require significant amount of training time, and are intractable for larger data sets. Also, the existing methods focus on single type of feature. So this is what the original paper of Rocket cites as their motivation for developing the new method. So building on the recent success of CNNs for classification problems, Rocket was presented as a simple idea actually mixed with a linear classifier to replace the traditional CNN that you have to tweak or optimize. So let's have a look at that. So the justification for the development of this work is that while the weights of convolutional kernels are typically learned, as we know, it is well established that random convolutional kernels can be effective. So what the authors are suggesting, they just say, okay, get a different number of kernels, let's say 10,000, 20,000, whatever, randomly initialize this, don't do any optimization or learning, just simply convolve these randomly generated kernels with your input signals and extract some sort of features that we are going to talk about today. And that should be effective enough for classification problems. So the authors also cited that, saying that CNNs exhibit high variance in classification problems on UCR archive, which motivated them to use ensemble of such architectures with a large number of variety of kernels. But if you want to go back into the history, Rocket is not the first method that employs random initialization of weights, and it employs them without any tweaking. If you go back in the literature, you will find extreme learning machine was actually developed so many years ago. It has one hidden layer, and it's typically initialized randomly, and there is no tweaking in that as well. So one hidden layer, you initialize it randomly with a large number of neurons over there, and then you multiply the input by the, let's say, weight matrix, which is random, and then you get very decent outcomes. So I see Rocket actually as a development on ELM, because ELM does not use kernels. It's just like giving you a matrix. So over there, it's like matrix multiplication, and matrix is generated randomly. There's no convolution process like happening over there, basically. But you can think of it as development of ELM. And ELM can also employ multiple hidden layers. So it's up to you if you want to employ multiple hidden layers, and these are also randomly initialized. So as ELM has been in the literature for a long time and people have been achieving significant outcomes with ELMs, the authors over here obviously were inspired by ELM, and they thought, like, what if we just develop a new version of CNN that's like, let's say, works like ELM, with random initialization of weights, and let's see how that goes on. So different from deep learning, all the hidden neurons in the hierarchical ALM as a whole are not required to be iteratively tuned. Keep that in mind. Now, back to Rocket. Rocket transforms the time series data using a very large number of random convolutional kernels. So what you do, you, let's say, generate randomly 10,000 kernels with random lengths, weights, bias, dilation, and padding. The transformed features are used to train a linear classifier. So after getting your features from like the result of the convolution process, you get a simple linear classifier and hook it up with the outcome of Rocket, and then you will be surprised how good the results are, basically. 4 things distinguish Rocket from typical convolutional layers in CNNs. The first is that Rocket uses a very large number of kernels. Second is that it uses a massive variety of kernels. Rocket makes key use of kernel dilation, and then basically it extracts 2 types of features. So one of them is the maximum value, and the other one is the proportion of positive values, PPV, as I will show you in a while. So here what you see over there is an example, actually 2 examples. One of them where we convolve an input signal with a short kernel, the red signal, and one of them where we convolve the signal with a long kernel, as you can see in this part of the graph. The result of this convolution process, so first of all what the convolution means is that get a function or get a small signal, as you can see over here, this is your kernel, randomly initialize it within Rocket, and then pass it by your original signal, and then every time multiply and add the values and generate a new signal, the green signal, for each of these 2 cases. What Rocket says, it says, okay, we did this convolution process, then what you need to do is to pick up the maximum value of the green curve, which you have generated by this convolution process, and then you also count the amount of positive values. So 2 features, the maximum of the green curve and the amount of positive values, what they call the PPV. So, sorry, the parameters of Rocket, as you can see over here, the length is randomly initialized to either 7, 9, or 11. The weights are basically Gaussian distributed. So it has a range between 0 and 1, normally distributed. The bias values will plus minus. The dilation will be limited by the length of the time series that you are actually looking at. And the padding can be positive or negative. And the features that you are extracting, as I said, will be the maximum value of this green curve and the amount of positive values. So you look at the curve, you see how many of the values were positive, how many negative, and then you build your ratio. Now, in comparison to Rocket, like we said, these are the parameters of Rocket. The same authors who developed Rocket came back with a new version called MiniRocket. So if you look at the parameters, what the authors said is they said instead of having these sort of parameters, let's just tweak them. So they focused the kernels on a length of 9. The weights are now generated to have only 2 values. It's either -1 or 2. So randomly initialize it and then pick up a threshold. Anything above the threshold is -1 and below the threshold is 2, or vice versa. The bias will be picked up from the convolution output, and dilation again is relative to the input length, and the padding as it is, and features over here will be only the PPV. They don't extract the maximum value within MiniRocket. So what is the impact of dilation? 3 examples over here that I picked up from the video by the original authors of Rocket. So you can watch that video over here, put the link over here. So what they say over here, if you have a dilation of 1, and this is your kernel, so with a dilation value of 1, when the dilation value is small, what you are doing really is that you are picking the local activity of your input signal. So if the input is the blue signal, you convolve it with a kernel with a dilation value of 1, you will end up with the orange signal, and over here you are picking up the local activity. If you enlarge the dilation value, you make it equal to 2, and this is the kernel. This is how it becomes different from the original one. It's like you're stretching it out. What you are doing really is going towards more global kind of activity. And that will be very obvious when you enlarge the dilation more into a bigger value like 4. And you can see that the result of the convolution, it's actually picking up the trend or the, let's say, global information of the input signal. In terms of the PPV and bias, so what's happening over here is that the algorithm is having a multiplication, like the input is multiplied by a set of weights, and then you subtract that with the bias. So if the bias is very like high positive value, this is the result. The most of the signal will be negative and a small portion will be positive, and this is the 0 axis, and you count the number of positive values for your PPV. If your bias is 0, then you push the signal a little bit, the resulting signal a little bit up. And if your bias is -5, it's like you're pushing it way more like towards the positive side. And then you count your PPV. So what Rocket is doing really over here is that, again, the input signal, the blue signal, as you can see over here, you generate a different, let's say, set or huge set of kernels with different lengths, as they say in the paper. So you can see they are all of different lengths. And then you basically convolve the input signal with these randomly generated kernels. You generate the results, the green signals that we talked about in a while ago, and then you extract your features, which are the max and PPV for Rocket. And if you move forward to MiniRocket, it's the same. So again, a set of randomly generated kernels, but now the kernels only have one of two values. It's either -1 or 2. You do the convolution again, generate the green signals, and then you extract the PPV. And they call this as a kind of pooling process, just like a CNN. And that's about this is it basically. This is Rocket and MiniRocket. Now, MiniRocket will give you a huge saving in terms of the training time, as you can see over here from the original authors. So they showed example where MiniRocket can give you savings up to 75% actually, which is very good. And you can try that yourself, and I'll show you some Python coding today, how you can do that, basically, how you can run Rocket and MiniRocket. Now, the most important part for me with this presentation, like beside the introduction of Rocket and MiniRocket, is this slide. So pay attention over here. We know historically that convolutional neural networks, they initialize the kernels with some sort of random values, and these kernels are optimized. If I want to look at what other methods exist in the literature, we previously said in one of the videos about wavelets, specifically wavelet scattering, is that wavelet scattering is a kind of deep neural network, a kind of deep convolutional neural network. However, the difference from CNN is that the convolutional kernels are not randomly initialized. They are actually initialized by the values of the wavelet families. And we have previously discussed that in one of the videos that we had before. So the kernels over here in this convolution process, they are wavelet-based kernels based on the wavelet families, and these kernel values, they are fixed, they are not optimized, unlike the CNN, where the kernel values are actually optimized. Now, if you bring Rocket, sorry, and MiniRocket, the kernels are also randomly initialized, as you can see over here, as we have mentioned before. So you generate them based on some sort of random numbers, and you leave them. You don't optimize, you don't tune. So just like the wavelet scattering, we have initialized our kernel weights by some approach, and we keep them fixed. So now the main difference between these methods are actually listed over here. So CNN, they initialize randomly, just like Rocket, that also initialize randomly, but CNN, they optimize these weights values. Rocket, they do not. Wavelet scattering, they initialize the kernels by the wavelet families, and they set that as the wavelet kernel values for convolution process, and they also keep them as they are, so they are fixed. In addition to these methods, there's a method that myself and my team developed earlier, and I spoke about that last year in one of the videos as well, which we call fixed convolution time domain feature extraction. We also initialize our kernels, like we also do some sort of convolution, but what we do over here, we just set it to unit values. So we set the kernel values, we don't randomly initialize, we just initialize them to be equivalent to 1, all the values of the kernels. And we leave them as they are, so they are fixed. So now you have 3 methods sharing the same category of fixed non-tuned weights for the convolution kernels, while over here you have a CNN which actually optimizes these values. So this is the main difference between all of these methods. Now, if you don't remember the wavelet scattering transform, I just put one slide over here to remind you. So wavelet scattering transform was developed like a long time ago, around maybe 2012 or even before, as a computationally efficient replacement to CNN. So wavelet scattering transform is not like the discrete wavelet transform or the wavelet packet. This is kind of like a deep version of that. The complexity of wavelet scattering transform is much lower than that of traditional CNN, because we don't need that many layers that we usually employ with convolutional neural networks, and we don't tune the parameters, so we save a huge amount of computational cost. So in a typical CNN, as you know, the layers are made of, let's say, consecutive repetitions of convolution ReLU pooling, and as you can see, convolution ReLU pooling and so on, while in the wavelet scattering transform, what we have over there is actually wavelet convolution, nonlinearity, and averaging, and we keep repeating that just like we do with the typical CNN. The other difference over here that, let's say, put wavelet scattering aside from other methods for signal processing, is that with the consecutive layers of decomposition, where you do your convolution processes, the first layer will actually give you a representation that look like Fourier transform, and then the second layer will give you a representation which is like the Fourier transform of a convolved signal. So just like deep CNN typically shows you, let's say, arcs, basic shapes in the first layers, and then as you move deeper to actually start picking up the more complete shapes like a car or face or something like that. Same thing happens in terms of the signals. As you go deeper, you go with like better representation of the underlying frequency spectrum and its energy. Going back just to remind you also about our own method, the fixed convolution time domain feature extraction. So I've spoke about this earlier. Unlike the existing methods based on CNN, so what we do over here, we assume that we have a problem with different signals, and at the time we tested it on raw EMG signals from someone implementing different arm movements. So you use a sliding window approach over here. You extract your typical let's say time domain features from each of the windows, like root mean square, the zero crossing, waveform length, etc. Then you simply reshape it into a 2D matrix, and you bring your kernel, which is made of ones, unit kernels, and you do your convolution process. The idea over here is that you are extracting the temporal activity from the windows by using different features. So each of the features will pick up some sort of that temporal activity, like a perspective of that temporal activity, and then this process, this convolution process, will actually give you a kind of spatial averaging, which is the average of the different channel activities. And then you apply some sort of attention and you flatten it and concatenate everything together. So again, you start with the raw EMG signals, use some sort of sliding window approach, as you can see over here. You feed that section into a, let's say, time domain feature extraction process. So for example, if you have 16 signals and you are extracting the root mean square, you will end up with a vector with a size of 16, as you can see over here. That 16, you can reshape it into 2D. So you can do it like 4 by 4, 2 by 8, or 8 by 2, or 16 by 1. And then you can bring your unit kernels and do some sort of convolution to get the spatial averaging of the activities of the different channels. And as we said, then you apply your attention or without attention, flatten it, and then repeat that process, extract as many time domain features as you want, and then concatenate everything together. And the other part of this method, so this fixed convolution method, the other part that we put at the end over here, we said after extracting these features, what we are going to do with them is that we are going to link the activity that we extracted from the current set of windows with the activity of the features extracted from the previous set of windows. So when like linking the activity of these windows with the activity when the windows were actually here, we were looking at the previous segment. And we put this graph at the time, so you can refer back to the paper and read more about it. Now, before I dive into the Python implementation of Rocket, I just wanted to remind you that the input format for the Rocket implementation, so basically if you have, let's say, a number of EMG signals or any kind of time series data that you have, doesn't have to be EMG, so you, let's say, use or extract, let's say, windows of these signals. So the input format would be the number of windows that you will end up having. So let's assume this is where the windows are here. Then you shift the windows there, and then you'll have another one. And then you continue building that up. So the size of the input will be the number of windows by the number of signals by the number of samples per window. And you supply that, let's say, data segment to Rocket or MiniRocket, and you get the features basically, which then you can send out to a linear classifier to give you the classification accuracy, or true positive, false positive, whatever measures you want to end up using. So at this point, I'm gonna stop the presentation here. I'm gonna switch to Python to show you how to implement this and get the code up and running, and then I will come back to continue the presentation. Now we are going to jump into Python to test the effectiveness of Rocket and MiniRocket on some real data. So let's start first by creating some virtual environment that we can install everything within. So let's create the virtual environment, conda create -n. Let's call it Rocket, and the Python version is 3.9. We'll wait for this to install the required packages, and then we'll take it from there. That's a yes. Hopefully this should be like, this would be actually quickly, so we don't have to spend a lot of time waiting for this. That's done. So conda activate Rocket. Now that we have created Rocket, we activated Rocket. Now we'll pip install skTime. So skTime is the library that already has the implementation of Rocket and MiniRocket within it. So we don't have to do anything ourselves. We don't have to implement it ourselves, I mean. We'll just use the ready implementation. We will also install the libemg from the New Brunswick University, where we have a dataset of, basically a library of EMG tools and data that we can try Rocket on. So let's wait for skTime to finalize its implementation. This will finish very soon, so we don't have to wait longer. That's done. Pip install libemg. And we might also need the Pi wavelets because it's used by the libemg. Maybe, just in case, I'll install it. For later tests. Let's see if we do already have numpy, which we should have. Pip install numpy. Sorry, numpy. Yeah, it's already satisfied. So let's go back to Anaconda. Now that we created the Rocket virtual environment, what we need over here is to get Spider installed, because by default, when you create a new virtual environment, Spider is not there. You have to install it. So install this within Rocket virtual environment. And the reason that I've installed everything in a virtual environment, because I want to contain everything in one place. I don't want this to affect my other existing libraries. So at the end of this demo, I can just delete the virtual environment and get back to my work on this laptop. Oh, there you go. So Spider, launch Spider, and we should see that coming up very soon. I didn't install the PyWavelet. I just want to check the code first for libmg. Okay, let's start first with the simple example. Let's say import numpy smp, and then from sklearn dot linear model import the classifier, which is the rich classifier cv. And then what we need basically is the data from sktime dot datasets. We will import load basic motions if it identifies that. Basic, nope, okay, load basic motions, so it's underscore motions. Oh, that's the mistake here, sktime. Okay, and then the final thing to load is from time dot transformations dot panel dot rocket. Oh yes, dot rocket. Import what? Rocket and MiniRocket basically. So I need rocket and MiniRocket. So that's all what I need to import. And now let's chop the data into training and testing parts. So that will be x underscore train, sorry, underscore train and y train. So the data and the associated class label, you will get that from load basic motions, and you will say split equals basically this will be train side, so train, and the return x underscore y equal true. And then similarly, let's copy this. This will be x test, and then this is y test, and this should be the testing data. So that's the testing data loaded. Let's put it like this, just in case we need to do that. Now that we have loaded the data, we need to instantiate a new rocket model. So I'll say rocket, let's say rocket equals a mini rocket model. I need the number of kernels to be equivalent, for example, to 500, and the random state, let's say it's 111, for example. Okay, so you will fit your rocket.fit on the x train, and then x train underscore transform equals rocket dot transform of x train. Okay, so rocket, and then what else do we need? So we loaded the data, instantiated a new model, and then we train the model based on the training data and we transform them, probably we can just bring x test transformed also here. So let's say this is rocket dot transform x test. So let's say here we will say instantiate the model and transform data. Okay, and the final part, which is the classifier R, classifier for rocket, is bridge classifier CV that we have actually imported. So let's say alphas equal mp.log space, and for this let's put the parameter between -3 and 3 and 10. Let's remove the extra brackets over there. All right, so this should be ready, and then classifier r dot fit on the let's say x train transform, and the other thing we need is the y train, which is the label. And beside that, all what we need to do then is to print the classifier r dot score on x test transform and y test. All right, what is this complaining about? X test transform. So that should be it. Let's try run cell. I want to do it one by one. Run cell. It's done. Run cell. This will take some time, but hopefully not much time. So this is MiniRocket, and we are only using 500 kernels, initiated randomly, no optimization, no tweaking, nothing. That's the only parameter that you need to set, which is the number of kernels. So once that is ready, we will actually test the classification accuracy, and I'm doing this step by step on purpose so I can show you, and run the last cell, and your accuracy is 1%, which means 100% accuracy. Now, if I go change this, let me try the accuracy of Rocket. By default, Rocket uses 10,000 kernels by default, but you can of course change it or just keep it on 500 kernels as we are doing over here. So let's do this again. We are running Rocket this time. Let's see the difference. So we got accuracy of 100 because this dataset is so simple, so easy to classify. It's not complicated. So I will test something more decent. So Rocket got 92, while MiniRocket got 100% accuracy. Not bad for a first try. But to be honest, what I'm mostly interested in is to do a test on the libemg. For that, what I'm going to do is go to the libemg, my electric, let's say. Let's go to this website. So this is the libemg, which we installed already. Library documentation is here. What I need is the feature extraction side. What the team from UMB has done is that they have tested a significant number of handcrafted feature engineering approaches, well-known features in this domain on this EMG dataset called 3DC dataset. This is an armband with 10 EMG sensors sampled at 1000 Hertz. And there are, I think, number of classes like hand movements, like 10 or more. And they are trying to identify these by using a typical machine learning framework with different features. I believe the best performing features over there that they have shown were the RMS phaser and the waveform length phaser. So we might be able to compare to those features. Let's get the code from those guys because they were very nice and put everything for us over there for free. Let's just grab this, copy, throw it over here, and then let's bring some parts of this code that we just created. Let me bring these. Okay, chuck this over here. You don't need that basic motions thingy because now we have our own data. And what they are doing, they are testing a huge set of features as you will see over there. So this is the feature list. Let's go to the feature list, see what do they have. As you see, it's a huge list of features which we don't really need it right now because they have tested it already. So what I'm gonna do is comment everything except one or two of them maybe. Okay, so tick, put this one over there. I only need RMS phaser. That's more than enough for our testing purposes. Close this. So now we have their own features. Now what I really need to do is bring the code for Rocket and MiniRocket and chuck it inside this code. So what this code is doing over here is that it's looping across the subjects and then across the feature list and then testing each of the features. What I really need to do is come down over here, push everything down, bring this part of the code, because I already have something similar to this, the chopping of the data into training and testing. They're already doing it in the same fashion, like this example. So I only need these two parts of the code to be copied, pasted over here. Let's see. So I have a rocket with 500 kernels. I am fitting the training data, and the training data is not called xtrain, it's called train windows. So train windows, and then transform train windows, and obviously it's going to be test windows. So this part is resolved, no issue. Then you define your classifier, and then your transform data needs a label. We don't have something called yTrain. Over here it's called something differently, so it's train metadata with class. So that's what you need over here. Chuck it in. And then X transform data also needs a label, so it should be test metadata. Okay, and that's what you need. Instead of printing it directly, you can put a print statement or chuck it in this results variable, because they instantiated or created an empty array to populate with the results as soon as they acquire that. So you can see results is a zeros, matrix of zeros that goes with the size of the feature list and subjects. So instead of the size of the feature list, what I can do over here, probably I can just, let's say 3, one for the root mean square phaser, and one for Rocket, and one for MiniRocket. So this was Rocket. I don't need this part over here. Let's bring the code together, and now result. Okay, you know what? I don't even need their own features at all. So how about we turn it off? I don't really need that part. I only need Rocket and MiniRocket. And I'll show you a comparison against their results after we finish, because this is going to take some time. So I'm only going to show you how to put the code and run it, and then skip the remaining part where it's waiting for the results to be generated, and show you that in an Excel file or PowerPoint slide. So chuck this over here. Let's say 0 equal this. I don't need a print anymore. I don't need that. So that's the testing data. Okay, this is using Rocket, and you need to adjust the size of this again, make it 2. All right, and then get another copy of this for MiniRocket, so we can see how Rocket is performing against MiniRocket. Okay, so this would be MiniRocket, and you repeat everything. You create this rocket model, you fit it with the training windows, transform the training windows and testing windows, and then you get a classifier, train it with X transform and train metadata, and then collect the results and put them in position 1. So 0 will be Rocket, and position 1, like the first column or first row, sorry, over here will be Rocket, and this second row, sorry, will be MiniRocket. And I'll show you the results after this code implements and finalizes. But I believe for this code to run, we also needed PyWavelet somewhere in the code. I'm pretty sure it was like that. I can double check and run the code. This might take a while, so I'll skip the remaining of this and just show you the results because I did that already. As you can see, it's actually asking for Pi Wavelet. You can go inside the code and comment it, or you can come back here and say pip install Pi Wavelets, and then let the code run and wait for your results to be calculated or collected, sorry. Once you do that, so I did that part already for you. This is all what you needed over here. Yeah, it's pretty much straightforward. And I'll show you the results in a while. And compare that to the results of the RMS phaser. I'll do that back in the PowerPoint slide, or can show you that in the raw format, because this is going to take some time. Thank you. So now that we have been through the Python coding section, and we showed you how to run Rocket and MiniRocket with the libemg toolbox, we acquired the results for running Rocket and MiniRocket on the 3DC dataset, and we have used the libemg toolbox and extracted the accuracies of so many features, basically, out of which I'm showing you here the accuracy of RMS phaser, as basically the graphs displayed by the authors of libemg show that root mean square phaser is one of the most prominent, or like really well behaved in terms of the classification accuracy. So as you can see over here, we have used 500 kernels only, randomly initialized them, and then extracted the PPV and the max with Rocket and PPV only for MiniRocket. And we didn't do any tweaking, nothing at all, no optimization. And this is the performance you get with something as simple as that, randomly initialized. So at this stage, you can see that basically the performance of Rocket and MiniRocket is not bad at all. Like, I'm honestly surprised by how good is this, given that it's actually competing with the RMS phaser, and RMS phaser is doing really well. Like, I've tested it on a couple of other data sets and it performs really well. If this method is kind of able to, let's say, compete with RMS phaser out of the box, no tweaking, no parameter selection. I didn't even tweak the number of kernels, which is the only parameter that you need to tweak over there. I didn't even play with that. I didn't even try different classifiers. My classifier was something very simple and naive, as you saw basically in the Python coding section. You can try different classifiers, more powerful one, and I'm sure you will get some really decent results. But overall, I would really recommend that you try Rocket and MiniRocket before you actually go and implement CNN or even temporal convolutional neural networks, TCN. So I would suggest give it a try, especially if you are working on CNN or TCN. And yeah, I believe you will be surprised by the performance. And if not, I'm happy if you can actually let us know about the outcome of your own experiments. And I hope that you have learned something new today. Thank you.